In our previous chapter, we learned how to start with one function, differentiate it, derive it, and get another function. We learned how to do this, and we learned what this meant for the original function. In this chapter, the chapter about integration, we are going to do the complete cycle. So we're going to start with this, considering a function which I called f of x. Note that this is a capital F. And in this particular example, I picked this quadratic. It is x squared plus 3x plus 1. We learned in the previous chapter that if we differentiate this, we will get this function f of x, lowercase f, which will be just 2x plus 3. I just applied here the rules of differentiation that you already learned in the previous chapter. Okay, but imagine now that we would start over here. Imagine that the only thing that you would get was this function. Would there be any mathematical way of knowing this function, get the original one, which is called, by the way, the primitive, hence the capitalized F that I used over here? Again, if starting with this function, is there a mathematical way to figure out what that was? This is the whole purpose of this first lesson about integration. We are going to learn how to start from here and get that. All right? Don't forget, last chapter, we learned how to go from here to here. Now, we are going to learn how to get from the differentiated function and get the primitive. All right? So let's use another example. Let me just say this. Whenever we do this, whenever we go from a function and get its primitive, we are integrating. We already got that from the title of the chapter. This process is called integration, and it is denoted in math by this symbol over here. It kind of looks like an S. You are going to understand in a bit the reason why this looks like an S, but you just use a symbol, you put the function that you are integrating, in this case it will be this, and you kind of close it with the dx. You are going to see the reason for this in a bit as well. So this notation over here just means that you are integrating the function that you have over here, whatever it might be. All right? So let's pick another function. Let's say now that we have this function y, that is called, x cubed plus 4. It's a cubic function. And this is going to be the primitive. Again, in this case, we are going to learn beforehand, we are going to know beforehand what the primitive is. All right? From the previous chapter, we learned how to differentiate this. So dy by dx is going to be what? It's going to be 3x squared just, right? So this is another function, the derivative of this over here, which is just 3x squared. This means what? This means that if we integrate this, we should get this function that we already know, right? If integration is the opposite, so to speak, of differentiation, then integrating a differentiated function should yield the original, the primitive function, right? In this example, we already know what it looks like. All right, so let's use this fact to try to figure out a way to integrate any function. So if we integrate this, so sign of integral 3x squared dx, what will we get? We will get x cubed plus, we already know that it is 4, but for now we are just going to write k, where k is a constant. I'm going to talk about this in a couple of minutes. For now, just accept my word and take it as being just k, a constant. All right? So what have we done here? Let's try to generalize what we did as we went from here to here. If we have any function in the form of x to the power of n, then if we differentiate this, we already know this from the previous chapter, that we will have n x to the power of n minus 1, right? So if we integrate now this, we should get the x to the power of n. So this means what? This means that every time we integrate a function in the form of x to the power of n minus 1 dx, we will get what? We will get x to the power of n divided by n plus a constant that we don't know yet. So, generally speaking, to round this up, I'm just readapting this to a more visual way of knowing things. Integrating a function in the form of x to the power of n dx yields x to the power of n plus 1 divided by n plus 1 plus k. All right? So what is happening to the power? It's increasing by 1. Remember in last chapter that every time we differentiate, the power goes down by 1. Well, when we integrate, being integration the antiderivative, we are going to bring the power up by 1. Dividing also by whatever the power we got there, right? In our exercise lessons, you have plenty of examples to practice with, and this will become as natural as breathing as long as you do the required number of exercises, just like you did for differentiation. Now you know how to differentiate in a heartbeat. You will also know how to integrate in a heartbeat. Note also that this representation over here, this encompasses all different types of functions that you can think of. This could be x squared, this could be x to the power of 5, x to the power of 1 million. This could be 1 over x squared. In that case, n would be minus 2. Or 1 over x to the power of 10. In that case, n would be minus 10. This could be cube root of x. N would be 1/3. N can be whatever you can think of, but the process is still the same. All right? It's very simple. It's literally as simple as differentiating. You just go the other way around. So let's look at another example, at this example over here. Let's say that we are integrating x to the power of 4. So applying this rule, what is going to happen to the 4? Is going to turn into a 5, and you divide by 5 plus k. All right? How can you be sure? If you are unsure about the process that you follow to integrate, what can you do? You can differentiate your result, and if you got the original function, the one that is being integrated to begin with, then you did the right thing. Okay? That's what I did over here. If I integrate this, I have x to the power of 5 divided by 5 plus k. K is a constant. What will I get? I will get to differentiate both of them individually. This will be just 1 over 5 times x to the power of the x to the power of 4 times 5. This 5 cuts with this 1/5, so I just get x to the power of 4. And this, being a constant, if you differentiate any constant, you already know that's 0. Okay? And now comes the part in which I talk about this k, right? If every time you differentiate a constant, you'll get 0, all right? If you are now integrating a function, there is no way for you to know without any extra information if you will have an original constant, a constant in the original function. You know what I'm talking about? Again, if you are differentiating a function that has a number in it, a constant, if you differentiate it, the function that is differentiated will have no information about that number over there. In this example, where is it? The one I just used. Let me see. In this example over here, every time you differentiate this, the result will have no information about this 4. Okay? So if you integrate this, you will always have to put this k, and this k represents any constant that might be in the original primitive function. All right? This k is called the arbitrary constant, and you always have to put it there. Okay? Now, I invite you to stop the video right now, if you will, and practice with enough questions so that you know how to integrate, because, again, you are using integration as a tool for the questions that will come after. Let me just go over some other very important 3 rules that you'll need to know. Now that you know about differentiation, I'm not going to extend much explaining the reason why these rules are the way they are. They stem from whatever I already explained when I taught you differentiation. But if you are to integrate a constant a times x to the power of n, you can just literally take a out of the integral sign and integrate whatever you are left with. Okay? If you are integrating the sum or the difference of two smaller functions, this being a function, but it's composed of the sum or the difference of two smaller functions, then this is going to be equal to the sum or the difference of the integrals of each one of the individual functions. Okay. And then you have the reverse chain rule. Remember the chain rule? That it was one of the last things we talked about in differentiation. Well, you have the reverse chain rule. So if you have a function in a form ax plus b to the power of n, in which a and b are constants, and n can be anything, all right? If you are to integrate this, the result is going to be this: ax plus b to the power of n plus 1 divided by n plus 1 times a. What is a? A is this bit, or actually the whole function over here, differentiated, the part that you have inside the brackets, all right, which is just a. See how similar this is to this? Okay. Obviously, plus k plus the arbitrary constant.